like the chalk sound is very loud. I don't know why.
All right, so let's
But it looks nice.
pick things up and let's go on the road. I don't know why this half of the classes disappeared, but you know, if you live, if you're sitting here, you're scared. Well, that's typical, yes. All right, very good. So, right. So all of the lectures and solutions to date are on the web, and the videos are there. Putting solutions to problem set 3 tomorrow. Yeah.
What lecture?
I think last lecture is on the
5. Yeah.
I think last lecture is on the web.
Everything is on the web now. I did it just before class. So everything should be there. If you're not, let me know. I'll make sure that. But I uploaded everything
You guys are talking about
just before
lecture.
class. So we are currently in lecture 5. Right. So problem set 3 is due. Problem set 4 is now available. It will be due in a week. All right. So let's see. So last time we wrote down the general solution to spin resonance, which is the problem, as we will emphasize today, of any two-level system that we're driving near resonance in different ways than a real spin. And we solved that problem by just solving the Schrodinger equation in the rotating frame picture. And we found the time evolution operator in that picture is, as it must be, because everything is of this form, a SU2 rotation. And the SU2 rotation is always the rotation by some angle around some axis. Okay? And the rotation is at an angular frequency, capital Omega effective, which has a transverse component and a longitudinal component, depending on the Rabi frequency and the detuning. And also this component, this transverse component, depends on the phase of the drive. Okay, so by varying the phase, we can vary the axis of rotation. And with that, we can write, this is the general form of a SU2, can always be expanded in terms of cosine of the angle over 2 and sine of the angle over 2, where the cosine has the identity and the sine has the Pauli along some direction. And that direction is the direction of this vector. And the direction of this vector is the vector over its magnitude. That's the unit vector. And so that gives us what this direction is. And from that, we got this general solution. So this is nice. It's the absolute general solution. And we see the probability to be in the excited state, which we got in lots of different ways in terms of just thinking about a gyroscope, but we see it also here in the Schrodinger picture in terms of the square of probability amplitude. It's the same solution looked at in different ways. And moreover, the relative phase between these components depends on the phase of the drive. Okay, so we have an oscillating drive, and what its phase is at time t equals 0 determines the relative phase between these two components. Okay, so, all right. Moreover, the last thing we talked about last lecture was the rotating wave approximation, which will take more poignance now. But the rotating wave approximation has its roots in spin magnetic resonance. And it's a geometric and physical thing. So the idea is if I don't have my transverse field that is co-rotating with the bare Larmor precession, but instead was oscillating, say, linearly in the transverse plane, then we still have spin resonance, but we can't solve this problem exactly anymore because we can't go into a frame where the Hamiltonian is time independent, okay? And because of that, but we can solve it approximately if this is true. So if this resonance frequency, the frequency which this thing is processing in the absence of a transverse field, is way faster than the Larmor precession rate, and also it's close to resonance, then effectively we can break up this linearly oscillating thing into a component that is co-rotating, and that is going to accumulate a lot of torque because it is co-rotating with this and will cause this thing to flip, whereas the thing that's going the other direction will just cause it to wiggle a little bit. It'll never accumulate any appreciable torque because it's completely out of phase, and we can think about it as a negligible contribution. And mathematically, if we were to try to solve the Schrodinger equation, what we would find is that in addition to our static term that we were able to then solve in the rotating frame, we would have time-dependent coefficients which would oscillate extremely rapidly compared to the time scales at which it would otherwise evolve. And there's a formal way we could solve that by solving differential equations with time-dependent coefficients and so forth. But the bottom line is the rapidly oscillating terms are negligible, okay? And it's just, but it requires this to be true, okay? All right, now, everything we've discussed up to this point, as you know, Tristan, you made the point in the last lecture, but this looks darn physical. It's just, you know, the torque of a spin in a magnetic field. But as we said, this is true no matter for any driven two-level system, any qubit. It's exactly the same. The mathematics is exactly the same as the evolution of a spin in a magnetic field. So let's talk about the problem of a two-level atom driven near resonance. Well, what does that mean? I mean, it doesn't even have to be an atom. It could be a molecule. It could be a quantum dot. It could be whatever system we have where we have a set of discrete energy levels that are sufficiently well resolved. And so, you know, I have some states, say in an atom. This is the spectrum of some atom. This might be the ground state, and this is the first excited state, and there are higher states. And we're then going to shine on a electromagnetic field to drive absorption, say, from the ground state to some excited state, okay? And we're off resonance by some amount. So there's I'll call it the light. So I have electromagnetic wave that is at some frequency of the light, whether it's optical microwave, UV, IR, I'm not saying for the moment. And it has, I have some electric field at the position of the atom as a function of time, which I can always write as the real part of some complex amplitude, e to the minus I omega t. So it's monochromatic for the moment. I'm just going to think about it as a single oscillating at a single frequency, okay? And that frequency is near resonance, meaning, you know, there's a resonance frequency, which is the Bohr frequency. Which is related to the energy level difference, and I'm near resonance, okay? And I want to describe the time evolution of the system in this context. Now, we could think about this in terms of absorption, stimulated absorption, but as we discussed, that's a little loose of a picture. We're not really, in this case, we know that we shouldn't completely, this is not the story of a quantum jump from ground to excited, but a more continuous evolution of the state, which would involve coherence. Okay, again, this name of the game, the story here is about coherence. And the fact that this is monochromatic is important for us to be able to have coherence. The reason that in the early days people didn't really think about this is that we didn't have coherent sources of electromagnetic fields, particularly at optical frequencies. It took the invention of the laser before anyone started. So the laser was really important when people really started to think about quantum optics. Okay? All right. Now, the story of two levels. Why am I calling this a two-level atom? Atoms have an infinite number of levels. Yeah?
You're only addressing one of the other ones?
What does it mean to address that? You're right, but how?
Maybe on resonance with one of them.
Yeah, or near resonance.
Yeah.
Okay? So we're assuming that I'm sufficiently close to resonance that only one other level other than the ground state or is sufficiently, what's the condition that that is true? Why wouldn't I get, well, this is not on resonance with this, but it's not on, why is it I can only consider one and not all these other levels at the same time? Yeah?
Because the other ones are far enough away.
They're way far off resonance. This is close to resonance. It's off, potentially off resonance, but close. So what's the condition? How far off resonance is far? How far off resonance do I need to be in order to say that this is negligible? Yes?
I was going to say you have a profile of probability so that you're sufficiently in the tails to where the probability is very, very low to be excited in that state.
But what is that probability? Well, there it is, right? In other words, if I'm sufficiently far off resonance, then this is going to be small. And that depends on the intensity. It's not just it depends on the intensity or something that has to do with the strength of this. So the Rabi frequency that connects these two levels has to be small compared to the tuning. And that's generally going to be true when, you know, if I'm way up here near the ionization threshold where they're close together, then I may have to be more careful, right? Because the energy levels get closer to one another. But the condition is that the effective Rabi frequency that would couple these two levels should be absolutely tiny compared to the detuning, okay? And that is an easy thing to...
I can see the intuition here because I can see how that the tuning matters because the tuning is like the energy of transition. But with the radio frequency, which is like the amplitude of the laser, I don't see how that those two relationships come together.
Well, the point here is that if I should think about this on the Bloch sphere again. If my Rabi frequency is like this and my detuning is like this, no, that's supposed to be the center of the sphere. Then my effective is almost the same as if I'm on right this, but if my detuning is absolutely huge compared to the Rabi frequency, I can't get out of the ground state. I just can't. There's just, so the idea of this business about energy conservation, I heard this discussion about virtual and borrowing energy from the universe. The point is, it's not an energy eigenstate of the whole system. So you shouldn't think about definite, there's this energy and that energy. There's an uncertainty in the energy. We're in an uncertain energy state. And that energy uncertainty, if it's sufficiently big, I can't, there's just no way I can get to that state. But if I cranked up the intensity high enough, I can totally excite up here. There can be a huge probability. Because if as long as I crank up the intensity, I make the Rabi frequency like this, I can drive off resonant population way up here. I don't have to be on resonance. I just have to have enough intensity to do that. I don't have to be on resonance to have high probability to excite up here. All right, good. So with all of that said, we then have a two-level transition, and we have to think about what is the, so my Hamiltonian, my atom in this approximation is this. That's the Hamiltonian of the atom. It's the sum of the energies. There are only two that I can have to consider. If I start the population, the ground state, and there's no way I can ever get to the other states. That's the two-level approximation. And what's my interaction Hamiltonian? Well, my interaction Hamiltonian is the interaction of the charge distribution of the matter with the electromagnetic field, right? Now, we have to write that down from first principles. However, because if we're looking at situations where we're not thinking about X-rays or gamma rays even, but we're thinking about optical frequencies or lower, the wavelength of the electromagnetic radiation is very big compared to the size of the atom. And under that condition, we can make the multipole expansion, Farouk's favorite, from last semester. And the multipole expansion tells us that we can approximate this as, well, there's a monopole times whatever the electric field is. Then there's an electric dipole dotted into electric field. There's a magnetic dipole dotted with it. There's quadrupole, etc., etc.
16 poles.
There's a lot of poles.
Some things won't
Right.
be because the first one's effective.
Yeah, that's not right. Times the potential. This is right. Times the electrostatic potential. Okay. First of all, this is a neutral atom that we're talking about, so the monopole term is zero. We're neutral. So and the other thing is these are properties of the atom. So this is all these guys are operators. We're treating the field for the moment as a classical field. We'll come back to the question of it being a quantum field in quantum optics. Yeah.
So I usually can kind of feel my way through what's an operator and what's not an operator. Can you have a E field that's an operator
Yes.
on a property? Okay.
Which we will talk about in a few weeks.
Okay.
So at the moment, we're treating the field as a classical parameter of course, every physical degree of freedom is a quantum degree of freedom, and there should be operators associated with all those degrees of freedom. We'll have to come back and say, under what conditions was it reasonable to neglect that and treat it as a classical field? But everything should be an operator if it's a physical degree of freedom.
We're just assuming we know E for sure.
It's the laser light that's coming out is well described by this. The quantum uncertainty will play a negligible role until we come back to it. Okay? All right, so now the question is, which one of these terms do we care about? And so this is the multipole expansion, and the multipole expansion requires that the wavelength of the light be much, much bigger than the size of the atom, which is about a Bohr radius. Okay? And under that condition, as we know from classical electrodynamics, the dominant term is the electric dipole term. So in the multipole expansion, we typically only worry about the dipole terms. We do, in principle, have to think about the correction terms, the higher order correction terms, but they are typically very small in this, for this condition, where this might be a half of an angstrom, a half of a micron, and this is a half of an angstrom, okay? So we typically make the electric dipole approximation when we are thinking about two-level atoms. Okay, so now we have to think about, we have restricted the atoms state, the atom Hamiltonian, to these two states. We want to write the Hamiltonian, that's the interaction Hamiltonian. I'll call the interaction Hamiltonian the atom laser or atom light interaction, as we often do, in the electric dipole approximation. Okay? And it's time dependent because the field is time dependent. Okay? And I want to write this restricted to this basis. Okay? So I'm going to just expand this thing by projecting it onto the two-dimensional subspace associated with the two levels of the atom. Okay. And so the question now is, we have to think about these different matrix elements. The matrix elements of the dipole operator. Remember, the electric dipole operator here is the charge of the valence electron that is being excited times the position of the electron relative to the nucleus. Okay? So we need to look at the we need to look at the matrix elements of this dipole operator. Yes?
So would R get a half then?
It does. It's the position of it's the thing that when we write down the wave function of a hydrogen atom, that's what we're looking at, the orbital, the position of the electron. Okay, so now let me ask you about the matrix elements. What is this matrix element? There's so many E's here. There's an excited state, there's the electric charge, the electron, I'm sorry, but that's just how it goes, okay? So this is the charge of the electron times the average position of the electron in the excited state. What is that?
0.
0. Why is it 0?
Symmetrical.
Because, and for the ground state, what is it? It's also 0. So why is that? Well, as Alejandro was saying, there's some symmetry here, right? Let's suppose this for the hydrogen, this is the 1s state, and this is the 2p state, for example, for hydrogen. The orbital, the 1s state, looks like this, and here's the proton in the middle. So we have an electron cloud, which is a sphere, and what's the dipole moment of that? Zero, because there's no separation between the positive and negative charges. And if this is the 2p state, it looks like this, where this is the proton in the middle, and you know, the wave function looks like this. What's the dipole moment of that? It's zero, because there's an equal probability always. If the electron here, there's an equal probability for it to be there. In fact, there's another way to see that, which is reflection symmetry, parity symmetry. If you look at the parity operator, which takes r to minus r, so the parity, the operator r is odd parity, which means if I were to think about this in terms of an integral, this is going to be zero if this thing is symmetric when I change r to minus r. So because these guys are eigenstates of parity, the states of the atom are unchanged up to an overall phase under the parity operator, the mean dipole moment in any of these states is zero. Which means that the only things that contribute here are the off-diagonal elements of this, right? So what I'm going to get in here is I'm going to get d Eg dotted into the electric field plus the conjugate. So I'll just write it like this. This dipole matrix element plus this dipole matrix element. So this is my interaction Hamiltonian, my atom laser or atom light Hamiltonian. And the only terms I have in this case are the off-diagonal terms. Okay? Why are they not zero? Sorry, Benny, you were there.
I was going to ask why two of those don't have any operator inside of them.
These guys?
No. Yeah, that.
I just did the projection, and this is the matrix element, and this is
Oh, that's one term?
This is one, this is a term?
Oh, okay.
I'm sorry, yeah. So,
Sorry.
no worries. Okay, so this I'll call DEG vector. It's a classical vector now. It's not an operator where I've taken the matrix element. Okay, why isn't that zero?
We don't necessarily. Sorry.
If you were to add the wave functions of E and G on top of each other, parts would cancel. It's no longer just symmetric.
Right. So if I looked at the superposition of those, I can see that I'm going to get a dipole moment because actually the phase of the wave function is positive here and negative here. They would add together in such a way that I would displace it. Absolutely, Tristan. There's an additional fact I want to just emphasize here is that these guys, if this is say a 1s and this is a 2p, then when I look at this matrix element, it would look like the position of the electron times the wave function of the 1s orbital and the wave function of the 1p orbital star. That would be, that matrix element is this integral. Everyone see that? And the question is, in order for this to be non-zero, this has to be an odd function of r, because this is an odd function, and I multiply an odd function times an odd function, I get something which integrates to something that isn't automatically zero. Is this an odd function? Yes, because this is an even function of parity, and this is an odd function of parity. So I have to have states of opposite parity in order for this matrix element to be non-zero. And that's what's called a selection rule. The selection rule says I can't go, if this is an S state, I can't go to another excited S state because they have the same parity. I have to change parity. And then I can have states that are connected. Yes?
So when Christian say, that would be true if you were acting it on the plus state.
That's right. Yeah, but it's the same intuition. It's the right intuition of what's going on. Okay, so that's just a little bit of atomic physics in the background to say whether the fact that we have a non-zero dipole matrix element will depend on the states that we're connecting. They have to satisfy the selection rules such that this matrix element is non-zero. If this were another S state. Now, I just mentioned, because this is related, Andy, to your question that you guys had about the current homework, which is, kind of just a little bit under the hood there. In the current homework, we're looking at this problem where I said there's this B field, and that B field's oscillating. And really what I'm thinking about is the problem of two states that are separated, not because there is a longitudinal magnetic field along some direction, but just because there's an energy splitting between them. For example, these are two states which are using an atomic clock, which could be in cesium. They're both they're S states. They're actually n equals 6. They have the same S, so there's no dipole, but they have a different total spin, F, where F is I plus J, I being the nuclear spin. That doesn't really matter. The point is that these states actually are connected by it's a magnetic dipole transition. It doesn't really matter for the problem. The physics doesn't really matter at all, except to say that there is an energy level splitting between them, and that energy level splitting between them. So let's go back to this problem now. So now I have my atomic Hamiltonian. My atomic Hamiltonian is but in my two-level approximation over here, I can consider this to be equivalent to a qubit, where this is, say, logical 0 or spin up, and ground is logical 1 or spin down. Let me emphasize, this has nothing to do with the spin of the electron. Nothing. It's just, we're calling it a pseudo-spin because it's a two-level system, and we typically call one of those guys spin up and one of those guys spin down. But it's really the excited state of the atom and the ground state of the atom. Okay? Yes, Nate, you had a question?
Should the second term be an excited state?
It should. So now, if I call this projection onto spin down, and this projection does spin up, I can rewrite this in the following way. Everyone see that? Give you a few moments to think it over. Because this is the projector on spin down. And this is the projector on spin up along Z. This Z has nothing to do with a physical direction Z. Okay? It's a pseudo direction. Everyone clear? Which I can write as some constant of the identity plus h bar omega Eg sigma Z. Everyone clear on that? This is equivalent to my longitudinal magnetic field. This mu is a fictitious mu. It's not the actual mu. It's not the actual magnetic field. It's just saying if I have any two-level splitting, I could have imagined it as like a spin 1/2 with a Zeeman shift. But this shift is not at all the Zeeman shift. It's the binding energy of the 1s state or the hyperfine interaction or whatever I like. Is everyone clear on that point? This energy level splitting plays the role of omega naught, the resonance frequency in our spin radius. It's just whatever the energy level difference is, that's my resonance frequency. I don't need no stinking longitudinal field to split something out. It's split by something else. Yes?
So in some arbitrary two-level system, we can find some physical process that looks exactly like.
There is exactly a magnetic field and an actual spin, which would be exactly the same two-level system. Okay, so the resonance frequency plays the role of the longitudinal field. And I don't really care where it comes from, it's just two levels. And let's take a look at this term now. What is this in spin in Pauli? What would I call this operator as a Pauli operator?
Now sigma.
Sigma plus. And I would call this sigma minus. Okay? So my interaction Hamiltonian here is minus d Eg sigma plus minus dGe sigma minus. Okay? And dotted into the electric field, which is, I'll say, some amplitude with some phase, e to the minus I omega t over 2. So that's the real part of this. The real part is that plus its complex conjugate over 2. That's what I wrote up there. Okay? I said it has an amplitude and a phase.
You're assuming the amplitude's real for this?
I put out whatever the phase is here.
Yeah.
Okay. Now, this could be complex as well if I had a complex polarization, but too many layers of complication. Let's take one off. Okay? And I can always choose the phase of the wave function such that this is a real vector. So I'm going to assume that, because generally this is the complex conjugate of this, right? Everyone see that? Because one has the GE, and if I take the conjugate, but I can choose it to be real. And sigma plus plus sigma minus is sigma x. like this. Okay? Now, if I look at that, this is just like our spin resonance problem with a longitudinal B field and a oscillating transverse field. It oscillates transversely. In this case, it's oscillating along what direction in the pseudosphere? It's oscillating along X. So it's like we had here, although that oscillation has nothing to do with the direction of the oscillation of the electric field. Nothing. Doesn't mean that the electric field is linearly polarized along the X direction. It does not. It just means that on the Bloch sphere, it looks like an oscillating pseudo B field. This could be circular polarization, and it would still look like that. Okay? So now I go into the rotating frame. Okay? If I go into the rotating frame, so my Hamiltonian is this and this. I go into the rotating frame. In the rotating frame, I rotate at the frequency of the laser. This interaction Hamiltonian will take the following form. DEG sigma plus e to the plus I omega LT plus sigma minus e to the minus I omega LT dotted into all of this.
Does
Yes?
that field always look like a linearly oscillating field? Like,
It does. It always does in a two-level system.
it never can be like circular.
You cannot. Yeah. In this problem, for a real spin, yes. For a real spin, yes, you can do that. Unless it's an actual spin 1/2 particle, you cannot. There is no way it looks like a linearly oscillating field.
So it's just an artifact of the formalism we're taking, building the effective two-level system.
That's right.
Okay, all right. Thank you.
So now, with that said, what you'll see is there are going to be terms that look like the following. I'll call this phi sub L, the phase of the laser. So this is my interaction Hamiltonian going to the rotating frame. The rotating frame, that U, is just a rotation around the z-axis at the frequency of the laser. That's how I go to the rotating frame, just like we did for the spin magnetic resonance problem. We went to the frame co-rotating with the rotating transverse field. Now playing and casting, the role of the rotating magnetic field is the laser. that gives me effectively a transverse field because this thing looks like something that looks like an X Hamiltonian, which causes a rotation around the pseudo X axis. Right? So, what can we say? What we can say now is that in the rotating frame, I have the co-rotating terms and the counter-rotating terms. And the counter-rotating terms are oscillating at this fabulously high frequency, say at 10 to the 15 cycles per second, compared to this, which might be 10 to the 6 cycles per second. And because of that, I can neglect that in the rotating wave approximation. And so what we have found when we put this all together is that the Hamiltonian in the rotating frame is now time independent when I have to take out, you have the Coriolis term, which gives me, I have to subtract out this. Sigma plus, yeah. Which is exactly the Hamiltonian we've been studying for the last number of weeks. This is exactly the spin resonance problem.
What are we missing a third?
What am I missing?
The first part.
Oh, I'm missing a sigma z. Thank you. This is equal to minus the detuning. Now, I could, if I wanted to, put in the identity there term as well, but for the moment, I'm neglecting it, okay? So what is the lesson? Firstly, what is the Rabi frequency here? I didn't even write it down when I dotted this together. What is the Rabi frequency? I had to take the dot product of that with that to get that. H bar omega is minus the dipole matrix element dotted into the amplitude of the laser. Okay. So the Rabi frequency depends on the dipole matrix element and the strength of the electric field. The strength of the electric field is proportional to the square root of the intensity. Okay, so it's proportional to the square root of the intensity. And so the two-level approximation is good if the intensity is low enough. If I had a, one of those, high pulse lasers, that was like a femtosecond pulse laser with a huge intensity, the two-level approximation ain't good because I can drive population all over the place. But, with some few milliwatts per centimeter square, this is going to be totally fine because we'll find that this Rabi frequency is maybe a few megahertz. Yeah.
So when you say the intensity is sufficiently low enough, I can also think of that as the line width of the laser being sufficiently broad.
No. The line width is about the frequency content. The intensity is just about the power. And it's true that I often have to squeeze more power into less frequency, but there's different parameters. How the laser distributes its power in different frequency components, but I'm talking at this point, and we'll get to it, absolutely CW laser with perfectly monochromatic, no line width whatsoever. And I'm just saying, how much power does that laser crank out?
Do you need to make any assumption about the phase stability of the laser?
Well, the phase of the laser is here.
Uh-huh.
So And in this case, if I had like a plane wave, then this phase is the k dot, the position of the atom. Okay, so it depends where the atom is, it will see different phases of the laser.
Thank you.
In this situation, are we going to consider the overall phase?
The overall phase is irrelevant. It's, I mean, it's what the phase of the laser is at the position of the atom. If I have two different atoms at two different positions, they'll see two relative phases. Typically, unless we had reason to think otherwise, we would just set this phase to be 0. But if we had the atom moving, we have to worry about where it is at different times, and we'll see different phases of oscillation of the laser. Okay? So, this is the story of the two-level atom. The story of the two-level atom is the role of the longitudinal magnetic field is just played by this. Whatever the energy level splitting is, that is effectively as if there were a Zeeman splitting between the pseudospin. And we have effectively a transverse field which has a Rabi frequency that is given by this. Okay? And then everything else is the same. If I started in the ground state, I will Rabi oscillate to the excited state. And I can make a pi pulse, and I could put the atom in the excited state by choosing this on resonance and having the time at which I drive it be pi. Or I could do a pi Rature pulse and put the atom in an equal superposition of the ground state and the excited state. And it will just Rabi oscillate between the ground state and the excited state with a frequency that is given, if I'm on resonance, by this frequency that depends on the strength of the laser and the matrix element. If I'm off resonance, well then we Rabi oscillate faster and we don't get 100% probability to be in the excited state. All right, is any of that, anyone have any question about any of that? Yes?
So suppose I'm off resonant and I have a digital.
Yep.
So where will the tuning come in Rabi frequency?
It doesn't, it comes in here.
Okay.
So remember the total Hamiltonian, and this is the same way we derive this, the total Hamiltonian is this minus from what we got the, going to the rotating frame, we had the Coriolis force. And when I subtract this from that, the total Hamiltonian is this. So this Hamiltonian for my two-level system is exactly what we solved for the spin magnetic resonance.
Could we do 3-level or 4-level the same way?
We're going to talk about 3 levels in a few weeks. It's about all we go to. So there is, the 3-level system has some interesting features. It's not all 3-level systems are isomorphic. In the context of a 2-level system, they're all the same because all we got is the identity, sigma x, sigma y, and sigma z. Every Hamiltonian is some amount of those.
Wait. Oh no.
Yeah. So, but for a 3-level system, I can have different kinds of interactions because I have more terms than just the Pauli's or things that look like the spin operators. So this analogy between a pseudospin and some number of levels in the atom stops at 2. It's not like a spin anymore at all.
Well, we could just look at it from the perspective of SVO3.
We could, but they're not. But those are not. They're not spin. Yeah.
And so, the sufficiently low intensity ensures that your H, whatever your omega is it is valid with regards to your
Right,
rotating
so
wave
I want,
approximation.
what I want is that omega to be much, much less than the energy difference between other. So if there are other excited states, I want this thing to be tiny compared to that.
Okay.
All right, we gotta keep moving. Good. So we have this now. Everything that we did for the spin magnetic resonance, we think about for our two-level atom. And so, for example, I can write down the what are called the optical block equations. What does it mean to talk about the optical block equations? Well, we have the block equations which told us how the block vector rotates on the Bloch sphere. They're the same equations for the two-level atom as they were for the spin, okay? And so in particular, if omega effective, let's say is minus delta in the z direction, and omega in the x direction, let's just take the phase to be 0 for simplicity. There's no reason to make life more complicated. And if we write the Bloch vector as having components, x, y, and z components that are Bloch called u, v, and w, then we can write down the equation of these three components of the Bloch vector. And what they are is du dt is equal to minus delta v, dv dt is equal to delta u minus omega w, and dw dt is equal to omega v. Let me check the signs of those things, because I can never remember it. And let me find it. Plus, minus. Okay, that's right now. Okay, so that's just this equation. It's another way of expressing the Schrodinger equation. But in terms of the Bloch vector, which are of course the mean value of sigma x, the mean value of sigma y, and the mean value of sigma z as a function of time as the system evolves. That's all we need to define the quantum state of the system, okay? And they're called the optical Bloch equations because now we're talking about optical transitions, but they're the same equations that Bloch wrote down in 1930 something. Oh, I saw this movie that my daughter made about it. Oh, you're from the 1900s. Anyway, so yeah, in the 1900s, Bloch wrote these things down. I'm definitely a person of the 1900s. Interesting. So now I want to come to the important point that we're having. At this point, all that we've said is that the system, we started, say, in the ground state, and if I'm on resonance, I Rabi oscillated. And I would do that forever. We know that's not true. we know that we lose coherence. Let me remind you for also, what are these components of the block vector in terms of the components of the density matrix? Because the state of the system is defined by the density matrix. Oops. Everyone see that? Sigma x is this operator, where this is like spin down and this is spin up. So this is equal to rho EG plus rho GE. Sigma y, this is the U component. The V component is this. Oh, I did it back. It doesn't really matter because this is the same. But when I bring it to the other side, that's rho GE plus rho EG. Not that it matters because it was real, right? If I take the trace. But now it's going to matter because that's where I just realized I didn't write it down exactly right. This is sigma plus, this is sigma minus over I. So this is rho GE minus rho EG over I. So this is equal to twice the real part of that off-diagonal matrix element, and this is twice the imaginary part of that. Right?
Yeah.
And so what it tells me is that this off-diagonal element of the density matrix is related to the components of the block vector this way. Up to this factor of half, the U component is the real part of this, and the V component is the imaginary part of this. Okay? So U and V are telling me something about coherence. How much coherence there is between these two states. Remember, the off-diagonal matrix elements of the density operator tell me about quantum superposition, whether I see interference. Okay? What about the W component? So that's the expected value of sigma z, which is the trace of rho with up minus down.
That shows the propagation.
Right? Everyone see that? That is my sigma z operator in the pseudo space, which is equal to rho EE minus rho GG. So the W component is about population inversion. How much I've inverted the population from the ground state. It's about the population difference. And the sign shows that if it's 1, if it's all in the excited state, it's -1, it's all in the ground state. So, when we look at the optical block equations, what we see here is that coherence drives population inversion drives coherence, and then I have, depending on the detuning, a kind of phase oscillation between them. So this is something, again, this abstraction I want you to try to absorb. We had this very physical picture of a spin, being cranked around like a gyroscope, but now we have a complete abstraction of two levels and their coherence between them evolving in this way that looks like the evolution of a spin, but is not a spin at all. Now, we know that it would sure be nice, we have our quantum computers by now, if coherence lived forever. And it doesn't. Moreover, if I'm in the excited state, I'm not going to stay there forever.
Well, it depends.
Nothing lasts forever but the earth and the sky. So,
you don't have a typo about transition, is it?
well, no, I mean, nothing is perfect. We will always have an added mixture of other things. Nothing lasts forever.
If nothing lasts forever, that means the ground state doesn't last forever.
It doesn't either. You know, the atom will, the proton, God knows how long nothing lasts forever. So, I'm sorry, folks, but that's the story of life. I'm getting closer to that story. Anyway, let me then say, so what do we do? Well, I mean, this is true also for the spins that Bloch looked at in the 1900s, where, you know, the spins didn't really process. They were in a liquid, they're in a solution, there's collisions, there's other stuff that happens that causes you to dissipate. And so we can think about this in sort of a simple phenomenological way of putting in a friction coefficient. In the same way that I had a classical simple harmonic oscillator, we know that, you know, the oscillator will damp. There'll be damping of the oscillation. That damping is coming from some microscopic phenomena, right? I mean, there's, you know, forces, there's a van der Waals force, things stick and unstick, but we don't have to get into that. We can just say there's a damping coefficient. And so that's what Bloch did, and that's what we're going to do too. And we typically write them phenomenologically as some kind of decay with some time constant that takes me down this way from in population, how the population decays. And we call that decay time T1. And then there's some decay in the transverse direction that brings this thing away from the Bloch sphere. We call that time scale T2. This is what Bloch called them, and we still call them that. So there's a T1 time and a T2 time in the same way, we just like we have put in friction. So we say, okay, the W's, well, this guy will decay with some T2 coefficient. This will decay with some T2 coefficient. And then T1, well, in steady state, we expect it to go to the ground state. So whatever the decay does in the absence of driving should take me to the ground state, okay? Which means that when this is 0, the solution should be W equals -1. So we write that as 1 over T1, W plus 1. Because if there's no driving, if the Rabi frequency is 0, in steady state, the solution is W is equal to -1. Yeah.
If we think about these decays as like we have a Bloch vector and it's rotating or just sitting there, it's gonna make it a mixed state, right? Like
It is. It is. Absolutely. Let's do that. That's really nice. Let's take so let me just Tristan, what you're saying is if we include the T1 and T1 and T2 decay, what is the trajectory expected to look like on the Bloch sphere? It's no longer going to stay on the surface. What do you think is going to happen?
I think it'll, well, just for T1, I imagine it's just going to be the Bloch vector will add a little bit of the direction, whatever's towards.
It's going to try to bring it down to the center. And the other thing is going to try to bring it in steady state if I had no driving, right? So if I had no driving, what happens to the U and V components in steady state? If I set omega to 0? It'll go to the R, it'll be, so what we expect, so if without damping, I stay on the surface of the block sphere and I stay a pure state. If I have damping, what happens is this. It doesn't go to the origin, because the origin is the maximally mixed state. The degree to which I have population inversion is going to be determined by how strongly I drive it. So if I have this two-level system and I start in the ground state, in steady state, I will have some amount of excited state and a tiny amount, and the steady state that I have here will depend on how much I'm driving it compared to the detuning. Okay? So this is the maximally mixed state is here, but in steady state, I'm not at the maximally mixed state. So let's just conclude here by writing down what we sometimes call the master equation, okay? We're doing this at the moment phenomenologically. We're not deriving the master equation from first principles at all. We put in a T1 time, we put in a T2 time, and we just said there are those decays, okay? And so with that, let's look at rho, the equation. So what we know, okay, let me do this one step at a time. Rho GE dt is equal to d by dt of a half. Okay? So let's just plug that in from our block equations. This is one way to do this. It's not necessarily the easiest way, but we can do that. So this is a half du dt plus I a half of dv dt. So that's equal to a half delta v minus 1 over 2 a half of u plus or minus I over 2 delta u minus I omega over 2 w minus 1 over T2 IV. Okay, just plugging all of that in. And so what do I get? What I get over here is I get minus I delta times u plus I v over 2. That's these two terms. I get plus I or minus I omega over 2 w minus 1 over T2 u minus I v, or u plus I v over 2. So this tells me that rho GE dt is equal to minus I delta rho GE plus minus I gamma over 2 rho GE minus rho GG minus, yeah, I'll put that over here. Okay, so this is one equation, and now I can look at the W's. And let me just write down the equations because we're out of time and I just want to just preview a little bit. Okay, let's take a look at these equations. I can't bring this up. All right. What do we see? These are the equations of motion of the elements of the density matrix. They involve coherences that are being driven by the population inversion and population driven by the coherences. Omega is related to the strength of the electric field that is driving the connection between the ground and the excited state, okay? We also have decay. We have decay of the coherences, and we have decay of the excited state. The excited state will decay. Where does it go? It goes into the ground state. Whatever change in the ground state, how much the excited state goes down, the ground state must go up, because this is a two-level transition with no leakage. The excited state and ground state populations must add to 1 at all times. This is trace preserving, okay? We obtain this equation is the master equation. This is saying that as an operator, this is the Schrödinger equation plus decay. We obtained this phenomenologically. I just threw in a T1 and T2 term and said, I'm not telling you where it just comes from. It's just there. Yeah.
I know you said it was phenomenological, but is there a reason why you have in the du dt term a 1 over T2u and not 1 over T2v?
Because it's exponential decay. In the absences, I'm just saying this decays exponentially.
But like in the duv term, you had both.
No, this guy
Oh.
is V, and this guy is U.
Oh, I see. I thought
So
that-
all of these guys are exponentially
I see.
decaying.
Okay.
This guy exponentially decays to 0. This guy exponentially decays to the ground state.
I thought that one of u was there too. Sorry.
Yeah, but this is about the detuning.
I see.
Excellent. Okay, so we'll just leave it there, but it's really kind of amazing how far you can get just with this phenomenology. What we will study next time is, what is the steady state of this equation? What does it get to? And we'll think about where T1 and T2 come from, at least a model for that. Well, I mean, yeah, I'm certain those are kind of, but what physically, why would this two-level atom decay? If I'm in the excited state, what happens? Does it just stay there?
No, but wouldn't
No, spontaneous emission.
But wouldn't that depend whether or not you're in a metastable state or not? How long that's going to stay?
Sure. So the rate of spontaneous decay will, I just say, it could be close to forever.
True. But not
Of course, never forever. But it could be close to forever. It could be, 10 to the 6th years before it decays, but it's not forever. Or it could be a nanosecond. That's not much close to forever. So fundamentally, T1 and T2 in an atom are coming from spontaneous emission. But there are other features, and we'll talk about those next time.
That's interesting.
All right. Have a good rest of your afternoon.
Homework 3 is the most fun I've had.